How many of you out there in the viewing audience have ever purchased something from a thrift store or similar establishment as an act of mercy? Hello there everyone, I'm uxwbill, and this clock radio is definitely an example of such a purchase. I have no idea what attracted me to it. It's not a tremendously featureful or unique unit. It's just a pedestrian General Electric clock radio. And while their clock radios were very solid performers for their time, and it would be hard to buy anything better even today, it's just not all that exciting. And when I was looking at this in the thrift store, I happened to plug it in just to make sure that it worked, and I discovered that it was completely lifeless. So I really can't explain to you why I bought it, other than maybe deep down somewhere I was thinking about the possibility of making a video like the one that I'm about to make right now. Here we are at the kitchen table, and this is not going to be so much a repair as it is a diagnosis video. That's right, we're going to have kitchen table electronics diagnosis. I don't know that we'll actually reach the root of the problem with this unit, but we are going to take a look at it, and along the way we're going to talk about some of the things that a person can do to diagnose electronics when they're just getting started out. A lot of people ask me about that, and I've never really put all my advice in one basket. I'm going to try to do that in this video. I'm also going to try not to forget anything, because when you've been doing this for as long as I have, it's very easy to just assume something, knowledge that other people may not have, and forget to mention something that might be of great import later on. So if I do that, I apologize. I'm going to try to be as thorough as I can. First thing I'm going to start with, yeah, it's great to know electronics theory, the ability to read a schematic, all those sorts of things, to understand what electronic components do in a circuit. In fact, when you get particularly involved in your troubleshooting, you have to know those things. But instead of starting out by buying $10,000 worth of test equipment and outfitting your workbench with every electronic component ever made in the history of ever, start out instead by using your common sense and your brain. That's right, think about things. Use your senses. Look at what the device you want to repair is trying to tell you. Because there are key signs. Does it smell bad? Does it look like there was liquid poured into it? Have you seen ingress of, say, pet hair, insects? Has it been dropped? Does it look like somebody's been into it before you? All those things are good things to consider, and there are certainly more beyond. Start with the analytical thinking before you haul out the first piece of test equipment. And that's exactly what we're going to do. We're going to start by unwrapping the cord on this. I wrapped it up pretty well. Either that or the people at the thrift store did. And we're just going to give this thing a once-over to see if there are any clues about its condition that might indicate what's wrong with it. Now, I should say that depending upon the age of an electronic device, it's not always a real brilliant idea to just plug it in and see what happens under uncontrolled conditions. It's certainly not a good idea with things like audio amplifiers just to blithely hook a pair of speakers up and assume that it'll work, or that if it doesn't, that the protection circuits will. Sometimes the people who design electronics, they make silly mistakes and they don't get fixed until a lot of very painful lessons have been learned. Sometimes they don't even get fixed then. For example, if the company that manufactured the device you have went out of business as a result of perhaps being sued for poorly designing a circuit or not considering some sort of edge case that caused problems for some people. So the first thing we do is we look at this thing and we see, are there any cracks in the case? Is there any sign that it's been abused? Are there screws missing? Does it look like there's been liquid poured into it? Does it look like it's infested with insects or pet dander or any kind of thing that just shouldn't belong there? Do the controls operate as they should? Can you push the buttons? And of course, getting back to the notion of just plugging a device in to test it, with something like this that's a relatively new product made within the last, say, 30 or 40 years, generally speaking, it's pretty safe just to plug it in and see what happens. But if you're looking at something from before 1970, you really should go over it and look at some of the passive electronic components before you just plug it in. Or you may take what was a minor problem when the thing was packed away in mothballs 50 years ago, and you may turn it into a huge morass. I know you will see people on YouTube that just take an old television set and they plug it in and they hide from the shower of sparks that may emerge. And a lot of times it doesn't. You know, you really got to admire what these electrical engineers can pull off when they design a circuit. I'm not saying they always think about how things are going to fail, but more often than not, things do fail more gracefully than they have a right to. But it's still not a good idea when you're just starting out. You may take a problem that was an easy repair, replacing capacitors, dealing with a transistor that won't oscillate, dealing with something else that's failed, bad solder joints, and you may turn it into an absolute disaster. And don't feel too bad about that if it happens, because you can't save them all. It's just not going to happen that way. Sometimes it's not cost effective to get the part you need. Sometimes you can't get the part you need for any price. And sometimes you just have to remember that not everything was worthwhile when it was first manufactured. So, with having performed a visual examination on this clock radio, I've looked to see if there's any signs of anything. I smelled it earlier to make sure it didn't smell like anything had burned, though that smell could certainly have dissipated. And I've also looked at the insulation on the cord set just to verify that it's intact. I've tested the prongs to make sure they're not wiggly and loose. There's no melting there. It doesn't look like anything's obviously wrong. So we'll just plug it in and we'll see what happens. I feel pretty safe in doing that, because a lot of times when something goes wrong with a device, sometimes it really is user error. Somebody got in a hurry, somebody didn't stop to think about something, maybe they brushed it against a pillow on their bed and they had no idea there was a control on the bottom that had some sort of an effect that made the device look absolutely dead. And you can see this thing is doing nothing right now. So we'll start out, we'll turn up the volume here and we'll try turning on the radio. Nothing happens. So maybe there is a more serious problem that merits going inside. But another thing we ought to do, we ought to look around and just see what kind of controls there are. By the way, here's the model information on this set. It is a 7-4652A General Electric clock radio, probably from sometime in the early to mid 1980s. Has that wonderful walnut grain finish on polystyrene, genuine fake wood grain that we all love so much. But here on the bottom, there's a brightness control for the clock display. And it's entirely possible someone could have turned that all the way down and made the display go dark. But in this case, it definitely doesn't seem to be what's going on. It's also possible that the cord set is bad. So another test you could run would be just to flex and abuse the cord, making sure, of course, that the insulation is not bad on it. Otherwise, you might have a very shocking experience. Come on, focus, camera. What is going on with you? But if you flex and abuse the cord and you find that the device flickers or flashes to life, yeah, you're probably dealing with a bad power cord. And that's another thing I wanted to try to touch on. The concept that everybody troubleshoots differently. Again, it's important to have a basic understanding of electronics theory, what components in a circuit are doing, why they are there, how to read a schematic, those sorts of things. But the most important thing is just thinking about what something is supposed to do, looking to see if you can find any obvious reason why it doesn't before you haul out the first piece of test equipment. So we've given this thing a pretty good physical once-over. I think we're probably safely to the point where we could haul out some test equipment right now and see if it can tell us something that might be going on. So here I am back with a multimeter to hand. This is not the multimeter I would normally like to use. Unfortunately, I do not know where my MS8229 multimeter got off to. I have not seen it in several months now. I hope I didn't leave it at a job site somewhere or at a project I was working on. I suspect it's probably out in the garage in some mess that I just haven't happened to look through yet. That was another thing I started to touch on. I think I kind of lost my train of thought there, which unfortunately is probably, going to happen during multiple portions of this video. Everybody troubleshoots differently. That's why if you watch someone on YouTube who takes you through a circuit and shows you what's wrong with it, as you learn, you may find your own way to do things, and I've certainly noticed that being the case in my HVAC class. Getting back to the diagnosis here, I have the cord set in hand, and the next test that I'm going to make involves the use of a multimeter. Now, I'm not here to give you the complete be-all, end-all tutorial as to how a multimeter works or what it does, why it does, and how you should interpret the results. But by necessity, we are going to talk about some of those things. The first thing we are going to do, we're actually going to make a voltage check. There's a reason for this. We just had this thing plugged into the wall. And we don't know but what there might not be a capacitor in there that's charged up full of electrical energy now. If I put my multimeter across these pins and I had it in ohms resistance mode, in the best case I'd pop a fuse. Maybe even nothing would happen. In the worst case, I might damage the logic circuits within the multimeter. In a really terrible case, like if I had it set to the ohms resistance scale and I plugged it into an outlet that was carrying electrical power, I might blow the thing clear across the table and be game over, be time for a new multimeter. Not to mention that it might also be time for a heart pacemaker, which I don't recommend. So since there might be an electrical charge present here, I just want to make a quick test just to verify that nothing's going on. Now we're in the DC volts scale right now, and it's showing 0.0 millivolts. We'll check AC voltage. There's nothing there either. So now what we know is that it should be safe to make a resistance test between the pins on this plug. Ohms is the unit by which electrical resistance in a circuit is measured, and an extension of the concept of ohms is that of Ohm's law. Ohm's law is a formula that allows you to determine any number of things about an electrical circuit, and it always works. For example, let's say that you know the voltage a circuit is being supplied with and the current that it's drawing. If you have those two values and you plug them into the formula behind Ohm's law, which you can look up online, I'm not hoping to get into it in that much detail here, it can tell you, for example, how much resistance there should be within that circuit. If you know the voltage and the resistance that it is being subjected to, which is really kind of a clumsy phrasing, you can determine how much current should be flowing across that resistance at that particular voltage. So if you know any two of the three relevant values, Ohm's law can tell you the third one. You can look it up online if you want to know any more. It's really quite fascinating stuff, and it is definitely a cornerstone of being able to troubleshoot electronic equipment successfully. Once you get past the point where your common sense has basically run out of gas and its usefulness has been exhausted, but that'll take a lot longer than you think. So I'm going to put my measurement probes across the pins of this plug, and I'm going to be very careful, A, not to let them touch one another, and B, not to touch them with any part of my body. Because right now, as you can see, we have a reading here on the multimeter's display of 292.2 ohms, and that little fraction of an ohm doesn't generally matter in a low precision application such as this. In fact, if I went and got another multimeter right now, you'd probably see that its reading differed a little bit. But the human body has resistance, capacitance, and conductivity of its own. And I can really screw things up at least some of the time by sticking my finger across the test leads, and I might not even know I was doing it. Now the human body's resistance is generally pretty high. You can see, although the readings changed a little bit, which again I'm not terribly worried about, hasn't made a huge difference. But let's say I moisten my finger and I stick it across those pins. I'm still not getting a change, at least not much of one. But sometimes you can end up precipitating a change and skewing your readings and thinking that there is a problem when there really isn't. So what's the multimeter telling me right now? Well, it's telling me that the chord set does have continuity. It's also telling me that the next thing in line, which is very probably what they call the primary winding or the line-connected winding of the power transformer, it's not completely open and it's not completely shorted. It does have measurable resistance. Is it the correct amount of resistance? I don't know that for absolutely certain. Again, I could use Ohm's law to figure that, or I could just take an educated guess for right now, keep it simple, and say, yeah, that transformer is probably okay. If you are fortunate enough to have service literature or a schematic for a device that you are working on, you could also see if it has anything to say about that, but it typically doesn't. I would say this resistance is probably a little high based on my experience, but it does suggest that there's not a serious problem here, at least not an immediately serious problem. So we'll go ahead and we'll turn that off. And I think we've done pretty much everything at this point that we can do without going inside to take a look and see what might be going on. And that brings me to the art and science of getting inside an electronic device. And getting into an electronic device is a lot of times much more art than science. In fact, sometimes it's almost a voodoo or a black art of kinds. Especially with newer devices where manufacturers love to use glue, snaps, and other things that you can't always open without totally destroying. And there are devices you can't always open without totally destroying them. Things that are encased in potting compound to protect them from the elements, or to keep people from repairing, or even to keep nosy people from figuring out how a given engineer actually did something because it's considered to be a valuable trade secret. A simple clock radio like this, though, is generally pretty straightforward to open. There's really nothing to it. You loosen the screws, and their condition, their level of tightness, can sometimes be used as a yardstick to tell you if somebody's been here before you were. Especially if any of the screws happen to be missing, cross-threaded, all sorts of fun things. They have mangled screw heads, that sort of thing. But with other devices, like I say, you have to be a little more creative sometimes. Manufacturers like to do all kinds of crazy things. One of their favorite tricks, especially in this particular vintage of device, involves placing a screw under a piece of trim. In the best case, you can remove that trim and put it back undamaged later on. In the moderate case, you can remove the trim, but it's kind of hairy and you have to be careful. And then there's the worst case scenario, which usually involves things like stickers, such as this date code sticker. Usually a sticker will form a piece of decorative trim, and a manufacturer will stick a screw under there. The cavalier and, shall I say, very, very unprofessional, hackish approach is just to jam a screwdriver through the decal if you don't care what the device looks like after you've examined it, especially if you think you're primarily examining it to perform some kind of a post-mortem examination. But you should always try, especially if you're working on other people's gear, to be as careful and meticulous as you can be. Put things back the way they were, separate your screws out into different containers. An egg carton is very, very handy for this sort of thing where you're likely to come in to multiple screws, multiple types of screws that aren't necessarily interchangeable with one another. So I've loosened all the screws. If we turn this over, I guarantee you a few of them are going to fall out. If we engage in percussive screw removal, a few more of them are going to fall out. And I think maybe this time, nope, there's just 4 of them that came out. I thought I might have gotten them all, but there's one that's very, very tight in its socket. And the case is indeed starting to come loose, which is a good sign, but we're not quite there yet, because everything is probably going to come out attached to this bottom panel, and that includes both the volume control and the tuner. And we have to figure out how we're going to get those off. Never ever force anything. If you're about to want to put your clock radio in a vise, it probably means you're doing something wrong. And if you pry with something like a metal screwdriver, you're going to leave visible marks that are very, very hard to get rid of. You usually can't get rid of them. You distort the plastic casing in such a way that there's just no turning back. And you don't want to do anything like that unless you know that your hand is absolutely forced. And again, manufacturers go out of their way to be incredibly irritating about this sort of thing. It would probably be best to use a plastic scribe to do what I'm about to do. I'm telling you that right now, so you can't roast me in the comments, or you can, but I won't care. I'll stick my fingers in my ears and go, la 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 la, I can't hear you. I'm going to take this butter knife, and I'm just gently going to pry these controls off. The tuning knob is probably going to present significant resistance. But even it too came off without too terribly much of a fight. And then we should be able, at least in theory, to open this up. Now don't just go and yank the cover off. In this case that would be a phenomenally bad idea, because as you can see, there is a speaker that is attached to the top cover, and it's got wire leads going to it. It also looks like there's some sort of a grounding lead that perhaps the manufacturers realized was necessary only after they started manufacturing these things. probably to help dissipate any electrostatic discharge safely away from the sensitive microelectronics and other components inside this unit when the user touches this top metal panel. So you wouldn't want to just rip the cover off. We'll start at the beginning. That's always the best place to start. I may actually take this speaker off to make this a little easier to work with, but the beginning in this case takes the form of a power transformer. And that's what this is right here. The power transformer takes the incoming line voltage, 120 volts AC here in the United States, and it steps it down to a much lower level, what is required by the supporting electronics of this particular clock radio. And since it is playing completely dead, we might as well start with something that's common to everything, and that is the power transformer. Now, I've talked about the transformer primary, which is the side that's connected to the AC power line. I've measured across it and I've shown you how to do that. We can only take a guess as to what the correct resistance ought to be, but we can probably also say that it's not completely open on that side. But there's another side to the transformer which isn't directly connected to the primary, and that is the so-called secondary. And the secondary side of the transformer is what's responsible for generating the lower voltages needed by the control electronics and the radio circuitry inside this clock radio. This looks to be what you'd call a center tapped transformer. That is to say, there's two hot leads coming out, and then there's a center tap in there. So, what are we going to do? Well, this transformer looks like it's actually been soldered down to the board, which unfortunately means it's probably going to be a complete pain to work with. But let's just go ahead and see if that's really true. It's held down with a series of screws, and it's entirely possible that I could be sorry after I did this, especially if those screws have like a nut or something on the other end of them. The nut could end up falling off. I may have to pull the circuit board out. I'll try this screwdriver. I think it's probably closer to being the correct thing, and I notice those screws aren't coming out, and unfortunately I don't have a magnet here, and they're going to be very difficult to grab by hand. We'll try this magnetized screwdriver and see if it'll bring them out. I brought that one out. Bring that one out. And we'll just see if this thing's actually soldered down to the board. Yeah, it's soldered down to the board, so if we want to troubleshoot it any further, if we want to have accurate results in our measurement, we're going to have to remove that from the board. I'm not really sure I want to get into that at 10 past 3 in the morning. Especially since in more recent times my desoldering iron has burned out. But I might pull the circuit board and just see how bad of a job that actually happens to be. We'll start by removing the speaker. I shouldn't have to back these screws all of the way out. At least the first 3 I won't, because they just connect to these little hinges that can probably, with some finesse, be pivoted out of the way. And I might have to remove one of them. Then we can lift the speaker away, and like most other top-mounted speakers, it's collected a dust bunny. Those can sometimes get down into what they call the spider area of the speaker, and they can cause a terrible scratching noise that makes you think the speaker's blown even though it's not. A good way to solve that problem sometimes involves just pointing the speaker down and leaving the device it's attached to playing at a moderate volume. Sometimes the dust bunnies will work their way back out of there. The other thing that we have to deal with is this little ground connection. And again, we'll probably have to desolder that, which I'm not really looking forward to doing. I'm not really sure how far I want to get into this. You know, I was going to make kind of a tutorial on basic electronic diagnosis and repair, but for something like this, you know, I'm sitting here and I'm having that discussion with myself about, is it really worth it to do this? And it may ultimately not be. But I'm going to go ahead and see what might be involved in getting that main circuit board out of there. I'm hoping that this top level board doesn't have to come off, because I'm not going to invest that much effort into this thing. So undo these screws. Let's see, here's a magnetic screwdriver is worth its weight in gold. Come Come on. There we go. I'll just get that one out by hand. Okay, there's a ribbon cable attaching that, so that's not the end of the world. Looks like there's a number of things that have to come apart here before I can get the main circuit board out. Looks like I have to loosen the clock display, which again is held into place with one screw that I can see. So I'll go ahead and I'll loosen these screws and get the onion a little bit further dismantled. I'll certainly give credit here where credit's due to General Electric's designers. They made it possible to remove the circuit board from this clock radio without having to disturb the dial stringing, and that's a very good thing, because if I'd have had to restring the tuning dial, I would have called the video off at this point and said, nope, that's the end of it, just not going to happen. So, what can we do now that we're looking at the component, at the solder side of the circuit board? I'm sorry. Well, as you can see, the transformer, which we'll zoom in on here, may have to recenter it a little bit on camera there, but you can see how the transformer is connected to the circuit board by 3 soldered points on each side. I'm not actually sure what all of these do yet because I haven't traced them, but it really looks to me like power comes into the transformer not through the circuit board, but from above by a set of jumper wires. Let's see if I can get that in camera here. And this looks pretty sloppy. This would definitely be an area of suspicion in my opinion. If we didn't get a resistance reading across here, I would be highly suspect of these solder joints. They don't look very good at all. And spotting bad solder joints is an art in and of itself. I can't possibly hope to tell you everything about it. Other than to say one thing to look for is anything that looks lumpy or gray. Solder joints should always be bright and shiny like the majority of these are. If they look lumpy, if it doesn't seem that the solder covers everything, you may be dealing with a bad solder joint, but I don't think that's the immediate problem here based on the results of our multimeter test earlier. And with multimeter tests and examination of a circuit, you should always make as many tests as you can with power off. Even if it's a battery device, it's always a very good idea to make as many tests as you possibly can with the power shut completely off. But let's go ahead and see what we might be able to find out here. We haven't noticed anything that's getting hot. The unit's completely lifeless when it's plugged in. We're going to make a test right now because I really don't feel like desoldering that transformer from the board. We'll just make sure that nothing can possibly short out here, that nothing is shorted out. We'll make a quick test with the multimeter just to try and confirm that. There might be a short on the secondary side, but that's unlikely to result in too many fireworks. Like I say, when you make multimeter tests, you should always make as many as possible with whatever you're working with completely disconnected from power. But sometimes you just have to make a test with the unit under power. So we'll plug it in here. And I would advise you to be very, very careful, because right here we have 2 points that are connected directly to the AC power line. If I take a reading off of those, you can't really see it. It's hard for me to get this multimeter within view of the camera, but if I take a reading off of either one of these, that's line voltage right there. That's 120 volts AC. In the best case, it'll give you one hell of a surprise. In the worst case, especially if you're not in the best of health, it will kill you. And it's never a bad idea to insulate the tips of your multimeter's testing leads so that just the tiniest little bit is left exposed, because accidental short circuits can really ruin your day. But with power coming into this thing, let's just see if there's any power coming out of the transformer. We have about 5 volts there. We have about 9 volts there. We have about 8 volts there. We have about 1 volt there. We have about 6 volts there. So our transformer seems to be working. It could be excessively loaded in some way. There could be a fault on the secondary side. But our transformer at least does seem to be functioning, and since it's not getting very hot in operation, it's not overheating, I think we can rule out the possibility of a hard short. We're just going to have to keep looking. And the next components that would be in line would be the rectifier diodes. And I have not verified this 100%, so I could be wrong about this, exactly where they are. But there's a diode, there's another one. There's one buried down in here. These probably constitute the bridge rectifier that's used in this unit. And it is proof that there is no accounting for the way designers like to make these things. They would ordinarily be, electrically speaking, if you drew a schematic, they'd all be right there next to one another in a sort of diamond configuration, but here they are definitely not. So let's just see what might be going on here. Here again, the best way to do this would be to desolder things, but I should be able, if those diodes are what I think they are, and I should be able to trace the circuit board and find that out, I should be able to go from each of these and go around and just see where they terminate and just see what I ultimately end up finding out as to where they go and if those are in fact rectifier diodes, as I think they probably are. Alright folks, it's gotten to the point where I have to admit I really don't feel like investing too much more time in this, especially since, as previously noted, the point of this video was to perform something of a diagnosis and to give those of you who are just starting out some ideas about things to look for, things to check out, that sort of thing. Things to think about more than anything else. I did finally find what appear to be the bridge rectifiers in this clock radio. We'll get the screwdriver here so I can point them out. There's two diodes there, and there's two diodes there. And just poking around at random in this circuit, here we have a 10-volt capacitor. It's got about 6 volts on it. That seems pretty normal to me. I'm not actually willing to pull these diodes off of here and test them, but I'm going to assume they're probably not shorted. There's also a component here. This is marked as an SGS Thompson part. That's ST Microelectronics nowadays. The only number it has on it is 1720. I've spent some time diddling around with that, running web searches on various permutations of the title. Haven't been able to find a data sheet for what that is. Don't really know what that is for sure. Don't really feel like investing the time to draw a schematic out for this, and I hate doing that because I'm not really very good at it. It does turn out, if we turn our attention to the computer over here, that Howard Sam's Technical Publishing does have a photocopy of the service manual for this set, but it also costs $18, and I haven't found anywhere to download it online. Although given the option to buy it, I would certainly choose to do that instead, because I want to keep a company like this in business, so if I have future needs for repair manuals and schematics, I would be able to get them. So I think I've pretty much decided to cut my losses on this, but there are a few things I've noticed. This is a 25-volt capacitor right here that you can't really see. Measuring across it, I've only got 2 volts. That kind of makes me wonder if something's being loaded down. This 16-volt capacitor right here, this big one, which I'd assume is probably a filter for the radio power supply if I had to guess, I noticed there's only about 230 millivolts across it. So something is definitely not quite right here, and I'm not totally sure what it is. But there is one thing I noticed that doesn't bring into consideration a multi-million-dollar price tag or a cast of 1,000 characters. The larger components in this set, like this large capacitor, have been glued down. And what can sometimes happen to this glue over time, it turns conductive and it creates unintended pathways between different unconnected circuits. There's a J17 here and there's a J18 there. And this is about as far as I'm willing to go with this. But I wonder, since this glue has gone from its normal white healthy color to this nasty black color, it sometimes also turns brown. And if you put a set of meter leads across it in the ohms resistance mode, you'll actually find that there's some degree of continuity. I really am not sold on the idea that this is able to leak enough electrical power to short something out or cause a major problem. But it is something simple, and it doesn't take very long to try it. We can clean it up. This isn't really the right way to do this, but it will work. We can just clean it up with a meter lead. I've seen this bring a switch mode power supply back to life before, and if you look very closely at these, they don't really show it too badly. I don't know if that'll actually decide to focus or not. But sometimes things that are exposed to this glue can become quite corroded and damaged in that way. So I think it's probably worth cleaning this up. And again, using a pointy meter lead probably isn't the right way to do this. But at this point, I just really don't care. I've said what I came here to say. There might be a little corrosion on those. But we'll just see if it makes any difference. I'll get things arranged here so I can actually power this up safely without risk of anything potentially shorting out. Fold that capacitor down, though not all the way because I don't want to touch those two jumper shunts. And we'll just see if it comes back to life. I have noticed that there are signs of heat stress here around the rectifier bridge and whatever this SGS Thompson component is, but that's really not too unusual. Those things emit a pretty steady amount of heat over the years, and you know, this thing's basically 33 years old at this point, 34 years old at this point. It was manufactured sometime around the 8th week of 1983, so it's had plenty of time to get settled in, I guess you could say. Anyway, like I say, we'll get things arranged here such that I know nothing's shorting out. I really don't think this will be the fix, but it costs nothing. I just don't want to put more into this unit than it's worth, and let's face it, it's not really worth very much. Come over here, try to find the power cord, and I'll plug it in. Yeah, I didn't think that would bring it back to life, and indeed it has not. Alright folks, here's the part where you knew I just couldn't leave it alone. I wasn't going to let this thing get the better of me, even though I decided it wasn't worth spending any more time on it. You know, I stepped through all this circuitry. I found readings that seemed at least plausible up to the point of this very large capacitor. Remember I said there were only about 230 millivolts across that, and it certainly acted like the power supply was being loaded down elsewhere in the unit. So I just really kind of began to get suspicious about that capacitor. I actually went ahead and clipped one lead off of it so I can take it out of circuit here. And I want you to see this because I think we found our smoking gun. The multimeter is in the resistance measurement mode right now and has an open loop reading. I'll go ahead and try to stick my test leads are all tangled up here. Alright. Now our multimeter's gone out of the way here so you can't see it. But alright, let's go ahead and put one test lead there. And what you should see happen, you should see the multimeter's testing voltage start to charge the cap. But you don't. You should see the resistance go up and up and up. Maybe even read open loop as the capacitor is charged. But you don't get that. That capacitor is basically a dead short. 0.08 ohms. So now I've clipped that out of there. Although this may not be the smartest thing to do, let's just go ahead and I have a hunch. I suspect that the circuit may not be 100% stable here. There may be an enormous amount of hum in the audio if I try to turn the radio on, because I've taken that big old filter cap out of circuit. And again, you could certainly shake loose some of that delicate silicon dust inside this thing if you weren't careful. But let's just plug it in and see what happens with that capacitor out of the picture. And look at that. That works. I suppose that if I turn the radio on, like I say, well, there's not a lot of hum. Let's see if it'll actually tune in a radio program. I must be on the AM band. See if the display dimmer actually works. Yeah, it works fine. Let me see if I can find the band switch on this thing and flip it over to FM and see if we get a slightly different result. Okay, after spending, well, rather more time than I'd care to admit looking around for the band switch on this thing, I actually discovered that although the tuning is analog in nature, the FM/AM band switch is actually controlled probably by the microcontroller that operates the clock. The darn thing works. And despite some of the things I might have said earlier about General Electric's product quality, it seems their engineers did a credible job considering there was a short circuit sitting across a significant portion of this thing's power supply, and all it did was just pull the thing down to the point where it wouldn't operate any longer. It didn't result in anything blowing up. That's actually pretty darn impressive. So I think the next order of business would be to order a 4,700 microfarad at how many volts capacitor? 16 volts. Put it in there and go again for many, many more years of reliable service. So thank you as always for watching. Even though this video certainly didn't turn out quite as I had intended it to, I hope it was certainly informative. Again, I would like to reiterate, be kind in the comments because I am not a professional. I do have a decent understanding of basic electronic theory, but there were certainly points in this video where I was scratching my head. But I think that just comes with the territory of being human and having to think things through periodically. And like I say, if you're just starting out in electronics, I do highly recommend it. Start with pretty safe stuff like this that doesn't work on particularly high voltages and is safely isolated from the AC line once you get past it. Just a little bit of a postscript, even though I said this video was finished. You know, if I'd have followed more closely with what I said and cast a more critical eye on the components inside this clock radio, I might well have actually noticed that the rubber bung on this capacitor is rather severely distended. It's been pushed out. It suggests that at some point prior to this thing shorting out completely, that there was considerable internal pressure buildup. I'm surprised it didn't come out the top, although the top is definitely not scored like it is on newer electrolytic capacitors. And this is actually a brand name part. This is a Matsushita Panasonic capacitor, rated for 85 degrees Celsius operation, and you know it can't have seen much stress in this application. So I'm guessing that it just had some kind of a latent defect, really, considering that electrolytic capacitors are nothing but rolled up paper and foil coated in some sort of an electrolyte solution that's usually of a proprietary nature. It's a wonder they're as reliable as they are. But that was definitely what was going on here, and I'll just have to order a replacement capacitor sometime. I hope you will all accept my apologies in advance if it seems like this video is just going on forever and ever and ever. But I thought it would be a good idea to throw in one last postscript, hopefully, and just go ahead and wrap a few things up. You see, there are two things I wanted to touch on. First of all, don't work on electronic devices or any kind of devices when you're way too tired to be doing so, or even if you're slightly tired. Your reasoning won't be working at full capability, and you may make a mistake that results in the equipment being ruined or an injury to yourself, and you don't want any of those things to happen. The second thing I'd like to talk about, I've been thinking about it today. Sometimes you just need to step away from these things and think about what's going on, especially if things don't seem to be making sense at that particular juncture. If that large capacitor that was defective that I removed was in fact responsible for filtering the power supply to the radio, it's very likely that anytime the radio was turned on, regardless of the volume control setting, you just hear an incredibly loud hum that swamped any trace of radio reception or anything like that. I actually think that capacitor was added because General Electric's designers realized they had a problem. If you look at the back side of the display board, and I'm not going to try to do this with the radio powered up, there is what looks to be a custom integrated circuit of some kind that is responsible for the timekeeping and radio power control functions in this clock radio. And what I think may have happened that necessitated General Electric's inclusion of that large capacitor, I think they may have discovered that there was an issue with that integrated circuit potentially locking up, crashing, latching up, whatever term you want to use, if there was a power anomaly that came along. Why do I think this? Well, to answer that question, we'll go ahead and turn our attention once again to the multimeter. I'll try to zoom in on the screen there so you can actually see what it says. And I want you to notice what voltage is present across the remaining stubs where that capacitor has been connected. If I can do this without getting my hands in the way, which may be quite difficult to do. And I don't want to inadvertently short anything here. But as you can see, there's about 9.3 volts across that capacitor. My guess is that is the power supply to the clock. It's probably also shared with the power plane for the backup battery, although I just now noticed this clock radio doesn't have a backup battery. So I think I have answered my question here. Maybe it's not so much a flaw in the design as it is a means by which ride-through could be provided for a power outage, which is really a pretty clever idea on General Electric's part. Since there's no backup battery in this clock, that large capacitor might serve to keep the clock memory going through a brief power outage. That's the only thing I had to add. I'd like to thank you for watching if you got this far. I certainly hope you won't jump to any conclusions in the comments before you've watched the entire video, but I should probably put that at the beginning of the video if I really wanted to make people aware of that. So I hope you've learned something from this video, if only that uxwbill doesn't always manage to pull things off as smoothly as it looks. But he does eventually get the job done, and at some point I will be ordering the correct replacement capacitor for this radio so it works as its designers intended. And I will put it back together in the meantime so that none of the parts get lost.
Put the load right on me.